We have seen that we can take the exponents of, for example, we have 2, we can raise it to the power of 3. And we can also raise it to the power of 0. And we have seen that if we raise to the power of 0, that's equal to 1. It doesn't matter what you raise to the power of 0, it's always equal to 1. As long as this is not 0, because 0 raised to the power of 0, that is not defined. We will not get into that at the moment here, but it's undefined. And we also have seen that we can raise to the power of negative numbers. And this we define just as this. So we see that we can take exponents of positive integers 0 and negative integers, or integers. But could we extend this? Could we, for example, take the power of a half? Or could we take, for example, power of 0.1, decimal numbers and fractions? And what would that mean in that case? So let's look at how we will have to define it if we want to also use powers where powers are not integers. For example here, 3 raised to the power of a half. What should we define this as? Yeah, we want to define it so it's consistent with other rules we had so far. So for example here, if I square this, is there some rule I can use, have before? Yeah, we know this rule that if you raise to the power of m and then n, you can multiply these two. So there's a rule that says that this is a half times 2. So that's one of the rules we had before. We didn't say that it worked for exponents that is not integers, but if we now want to extend it, we want the rule also to hold for non-integers. So what this becomes is 1. So this becomes 3. So we see if we want to define two powers that are not integers, then 3, for example, 3 to the power of a half, if you square that, we will get 3. But is there some other number, if we square it, that will also become equal to 3? Here we have a number, you square it, it becomes equal to 3. Is there some other number, if we square it, is equal to 3? Yeah, there is. Per definition, there is the number square root of 3. Square root of 3 is the number you should put here to equal to 3. Per definition, square root of 3 fits here. So we see that if we want to have this consistent, then square root of 3 must be the same as 3 up to a half, because both, if we square both, we will get 3. So we need to define, to make the rules consistent, we need to define this as square root of 3. Or if you like, since this is implicit, there's a 2 here. In a similar way, we could extend this to, for example, if I have 3 raised to the power of a fourth. What should that mean? Yeah, then you will see that this has, to make the rules consistent, this we have to define as the fourth root of 3. So if we want to define powers with non-integer exponents, then we need to define it as we have seen so far. For example, a raised to the power of 1 over n. Now we have a fraction here, 1 over n. Then we need to define this as nth root of a. So this is a definition. So we need to define it in this way if we want to make all the rules consistent. And follow along in the similar line if we want to have a fraction m over n, for example. Then we need to define this as, to make the rules consistent, square root of the nth root of a raised to the power of m. Or if you like, you need to define it as a up to 1 over n raised to the power of m. So this, you need to define it like this or that. So if you want to make all the rules consistent, and if you want to have rational powers, then you need to define it in this way. So let's see some examples. For example, if you have 9 raised to the power of a half, then per definition this means the square root of 9. So that's per definition. And the square root of 9, we know that it is 3. Or for example, if you have 16 raised to the power of 1/4, then this should be equal to the 4th root of 16, and that's 2. And we can also continue, like for example, if you have 8 up to 2/3, then we just look at this definition. What should it mean then? Yeah, per definition, this should mean 8 up to 1/3, if you look at this step, raised to the power of 2. So according to this definition here. But what is 8 raised to the power of 1/3? That's just the 3rd root, or the cubic root of 8. And the cubic root of 8, that's just 2. And raised to the power of 2, so this is 4. So we see that 8 raised to the 2/3 is equal to 4. Now also all the rules will work for, that we have gone through so far, will also work for rational powers. So for example, if I have 3 raised to the power of 1/4 multiplied by 3 raised to the power of minus 1/3, half, then I can use all the normal rules we've gone through so far. It will also work now for rational exponents. So what can we do here? Yeah, since the same base, we know that there's a rule for, we can just add these two. Or since we have minus, we can just subtract them. Since adding a negative number is just the same as subtracting. So here is 1/4 minus 2/4. So then it's normal fractional calculations. This is minus 1/4. So what can we do now? Minus, we know that this means 1/4. So this is 1/4. And this is the 4th root of 3. And here we can use a calculator to calculate that. So the 4th root of 3. And if we put that into a calculator, we will get this equal to 0.76 if you just make 2 decimals. So now we can make all powers of rational exponents. For example, what do I have if I have 16 raised to 0.25? Can I calculate that? Yes, since 0.25 is a rational number, meaning that I can write it as a fraction. So I can write it as a 4th. Then I can calculate it, because this now means the 4th root of 16. And what is the 4th root of 16? That is what we should multiply, we are raised to the power of 4 to get 16, and that must be 2. So 16 raised to the power of 0.25, that's equal to 2. And whenever we have an exponent, so whenever we have an exponent that has a finite number of decimals, or if it has a decimals that have a periodic sequence, that is, if we have a rational number here, we can always write it as a fraction. So if we can write this as a fraction, then we can calculate it, because we have defined it now for all fractions here. So then the question arises, what do we do if we have an irrational number here, if we don't have a rational number? So how can I calculate if I raise to the power of an irrational number? So can we have an example of an irrational number? Yeah, a typical example is pi, for example. So if I raise a to the power of pi, so this is irrational, so we can't write this as a fraction, meaning that we can't use our definition so far. So what should we do? Yeah, we know that this should be equal to, or is equal to 3.1415 and infinite many decimals. So this should be roughly equal to a raised to the power of 314. So if you round off to 2 decimals, this should hold. So it depends on how close to the real value we want to have, then we should round off here to number of decimals. So if we want to have it close to the real value, we take more decimals. But let's say that we are satisfied with 2 decimals. Then we can write it like this. And now, since we have a finite number of decimals here, we can write this as a fraction. So this we can write as 314 over 100. And now we can calculate it, because this power here is a fraction, a rational number. So then we have a definition how to calculate it. So whenever we have an irrational number, we just estimate it with, or round off to finite number of decimals, depending how close we want to have. And then we can calculate it. Then of course we can just continue to have more and more decimals, then we have a bigger and bigger fraction, and we come closer and closer to the real thing. So this is in practice how you can calculate it if you want to have an irrational exponent. So now we have seen how we can make powers of all kinds of numbers. So now it could be any kind of number, that means any real numbers.